Hi darlings, welcome to our video on molecular versus empirical formulas. So you will need your pen and paper for notes, a calculator, your periodic table, table T, and then if you forget how to name things, tables P, Q, and R will help you out. So for the periodic table, what we're looking for today is actually going to be the mass. So look at the key right up here and see where they give you the mass. So our masses are listed in the upper left-hand corner. Most of the time we'll just need hydrogen, oxygen, and carbon for today, and for many of our elements that we'll deal with. So it's kind of easier. You'll get to know what the masses are for each of them. For hydrogen, it's 1.00794, and you can round that to 1 for today only. There are some times when we can't round. Carbon is over here. It's 12.011. Again, you can round that to 12 today. And then oxygen's over here. It's 15.9994, and you can round that to 16 for today. You'll also need table T. Now we haven't seen a lot of formulas from table T, but the ones that we'll deal with today are mole calculations. So the number of moles is equal to the given mass over the gram formula mass. Unless you're watching this towards the end of the school year for Regents Review, you probably don't know what moles are. For today, just think of it as the ratio, or to help you figure out what the ratio is. The given mass will be given to us in the problem, and the gram formula mass, that is the mass from the periodic table. Okay, so make sure that you label your table T right now, or just write that out in your notes. Okay, so again, for the mole calculations, we'll just need them for ratios. The given mass will be usually given to us in the problem, and the gram formula mass is the mass that we just saw in the periodic table. For carbon, it's 12 AmU per mole, oxygen, 16, and hydrogen is 1. We'll also need to know percent composition. So percent composition will just be the percent, which is equal to the part over whole times 100. In this case, we're dealing with mass. So the mass of the part, that can usually be found from the periodic table, the mass that I just showed you for carbon, hydrogen, and oxygen. And the mass of the whole will generally be given to you in the problem. Don't forget to multiply by 100. So molecular formulas, we've seen them before. They're covalently combined, or they have covalent bonds, and they show you the actual ratio. They show you how many carbons, hydrogens, oxygens, and other elements are listed in that compound. Empirical formulas are actually just going to be the whole number, lowest whole number ratio. So we're going to reduce down the subscripts. So an example of a molecular formula will be C6H12O6. You remember this as glucose from back in bio. And let's go ahead and write its empirical formula. So we know it still needs to have carbon, hydrogen, and oxygen, but we're just going to reduce down the numbers to the lowest whole number ratio. So here we have 6, 12, and 6. Each of these numbers can be reduced down by 6. So that gives us 1 carbon, 2 hydrogens, and 1 oxygen. So the empirical formula of C6H12O6 is just CH2O. And some elements or some compounds you'll find have the same molecular and empirical formulas. For example, CH4 methane, its structural formula looks like this. And we can't reduce this down any further. So it's just going to have the same molecular and empirical formula. So for example 1, we have to figure out which of the following is an empirical formula. And again, we want to make sure that we go back through. Empirical formula is the lowest whole number ratio. So can we reduce down any of these answers anymore? If we can, then they're molecular formulas. If we can't reduce them down, they're empirical formulas. So for A, we have a 1-to-1 ratio. That's the lowest whole number ratio that we can have. So that would generally be an empirical formula. B is C2H2. We can reduce both of these down to CH, so this would be a molecular formula. C gives us C2H4. That's a 1-to-2 ratio, so that's 1 carbon to 2 hydrogens. So this is the molecular formula. This would be the empirical formula, so this is not correct. And then D, we have C4H8. Well, the 4 and the 8 can still get reduced down to CH2. So this is a molecular formula, this is an empirical formula. So now there's B, C, nor D are correct. A is our correct answer because it's already given us the lowest whole number ratio. So for example 2, which pair of formulas correctly represents a molecular formula and its corresponding empirical formula? Molecular formula will just be the ones that have the actual numbers. Empirical will be the reduced down numbers. And it should be the reduced down for each one of them. So go ahead and take a second, pause me, and figure out if you can go ahead, or if you, when you reduce down each of the first ones, if they will equal the second response. Alright, so let's take a look at A. C2H2, we can reduce down C2H2 to CH. So this is the correct empirical formula for this molecular formula. Let's take a look at B, C3H4. We can't reduce that down any further, so that is not a molecular, that would not be equal to this as an empirical formula. For C, we have C4H6. This can be reduced down to C2H3, which is not equal to this one, so that's not a choice. And then D, C5H8. That cannot be reduced, and this would not be the molecular or the empirical formula for it. So A is our correct choice. For example 3, which is the empirical, or what is the empirical formula for this compound? So just like we did before, we're going to go ahead and write down how many carbons, hydrogens, and oxygens this molecule has. So we have 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and 2 oxygens. Now, what I just wrote down, is that going to be the molecular or the empirical formula? If you said molecular, you're correct, because it is not reduced down yet. So we want to reduce this down to get to the empirical formula. We can reduce or divide each one of these by 2 to give us carbon, or C, H3O. So this would be the empirical formula for this structure. For example number 4, the molecular mass of a compound of carbon and hydrogen is 42. Its empirical formula is. So it's telling us that when we have these carbons and hydrogens together, if we add up the mass of the carbons and hydrogens, that gives us the number 42. We want to know what the empirical formula is. So here we're going to need a few things. We will need the periodic table to remember what the masses of everything is, and we'll also need our calculator. So I have my calculator in the upper left. Make sure you have your calculator here as well. So the easiest thing that I do here is actually check to see what the mass would normally be of each of these answers. So for A, I have carbon, which is 12, plus 1 for hydrogen gives me 13. Go ahead and add up the masses for each of the following. B would be equal to 14. C, we have 12 for a carbon, plus 3 hydrogens, because each hydrogen is equal to 1, so we can just multiply 1 times 3. So that gives us a mass of 15. And then D is CH4, so that's 12 plus 4, because the mass of hydrogen is just 1, so that gives us 16. So these are the masses of each of the empirical formulas. We want to see how many of them can actually go into 42 evenly. So what we'll do is we'll take our calculator and multiply. Oops, I don't think my calculator will show up, but you guys can do this. You'll actually divide. So you'll take 42, divide by each one of these. So go ahead and take out your calculators and see what would give you a whole number. So for A, if I divide 42 by 13, that gives me 3.23. It's not quite a whole number. Let's see if we have anything else that's a whole number. For B, 42 divided by 14 will give me 3. That's a great whole number right there. For C, 42 divided by 15, and you might hear my calculator in the background. I'm still typing away. That's 2.8. That's not a whole number. And 42 divided by 16 will give me 2.625. So B ends up being a whole number when I take the mass, the molecular mass, and divide it by the mass of the empirical formula. This one can get a little confusing, so tomorrow when you have these examples, just raise your hand calmly. I'll come around and help you guys out. Alright, oh, there's my calculator. Alright, so example 4, let's see, we just did that one. So example 5, a sample of a compound contains 24 grams of carbon and 64 grams of oxygen. What is the empirical formula? So for this one, we're going to need our formula for mole calculations. And we'll also need to know what the mass of each of the elements are. So I'm going to actually erase that periodic table. We'll bring it back actually. So let's see. If we have 24 grams of carbon and 64 grams of oxygen. We're going to take this mole calculation right here. And again, we just want to know the ratio. So the given mass is the ones given to us up here, divided by the gram formula mass. The gram formula mass is the mass that you'll find in the upper left-hand corner, and for today you can round it. So carbon will be 12, oxygen will be 16. So we have to find out what each of these are separately. So let's start out with the carbon. We know carbon is 24 grams. That's the given mass. The gram formula mass is 12 grams. So that's 2. So I know I have to have 2 carbons. And let's do the same thing for oxygen. Oxygen is 64. Okay. So that's the given mass given to me from my question. And then we'll divide that by the gram formula mass, or the mass from the periodic table. And we can round that for today. That's going to be 16. Divide the 2, and you should get 4. So we have C2O4. Now, the question wants the empirical formula, meaning the lowest reduced whole number ratio. So we can still reduce this down to be CO2. And so this would end up being our answer. Again, this can be a little confusing, so make sure you raise your hand, wait for me to come around. If I'm working with another group, then just move on to something else that's a little bit easier. All right. So for example 6, a compound is 86% carbon and 14% hydrogen by mass. What is the empirical formula? So we're dealing with percents here, so I need to have the percent composition. I need the mass of the part over the mass of the whole, and then multiply that by 100. So I know that 86 is my percent, so that goes on the left-hand side. I'm going to do carbon and hydrogen separately. So 86 is my percent, and we want to know what the mass of, we have the mass of the part over the mass of the whole. So the mass of the part is just going to be what the molar mass is. So the molar mass for carbon is 12. We don't know the mass of the whole yet, that's our unknown, and then we'll multiply this by 100. So let's rearrange our formula so we get x by itself. We have x is equal to 12 over 86 times 100, and go ahead and put this into your calculator. You should get about 13.95. I'll round that up to about 14. Okay, so I know carbon will be 14. Let's do the same exact thing for hydrogen. Go ahead and pause me while you go ahead and do the that formula for hydrogen. Right, hopefully you paused me and figured it out on your own. You have 14%. The mass of hydrogen is 1 over our unknown times 100. When we get x by itself, we have 1 over 14 times 100. And so x should be equal to, punch this into our calculator, 7. Okay? And so we know we have C14H7, and we want the empirical formula. So can we reduce this down? We sure can. So we have C2H. And so this is our empirical formula. Alright, to summarize, molecular formulas have the number of actual carbons, hydrogens, and oxygens, and other elements listed in the formula. The empirical formulas are the reduced whole number ratio. You will need to do some calculations, so make sure you have your calculator with you when we're going through this. Dig that out, find that, and we'll also use those 2 formulas that we looked at Table T and you'll need your periodic table. So make sure all of that is out when you're working on these problems. Take care and have a great day.